In this video, we continue with volume by revolution, and we continue with the same problem that we started with in the first video. Find the volume of the solid form by rotating the region bounded by the graph. 1 plus the square root of x, the y-axis, and the line y equals 3. We're going about the line y equals 5 this time. So the first video, we did the y-axis around the y-axis and around the x-axis. That created a disk and a washer. This one, we'll do another washer. So here's our picture. This is our y equals 1 plus the square root of x again. And then this is y equals 3. So we're talking about this little section here. And in this case, we're circling around this line. So we're taking this shape and spinning it this way. So it's going to create like a volcano looking thing, something like this, where the outside of it will be slanted, the inside of it will be hollow, or like straight and hollow. There's going to be a whole section of it missing, where if you picture, it looks kind of like a volcano, and we could slide like a soup can right down the middle. It's cylindric right in the center. So there's a huge gap, huge, like from here to here is 2 units, and it'll be the same on this side. So it's like a 4-unit gap all the way around. The diameter of the inside would be 4. So this is another washer situation, which means we're dealing with this formula again. You take the outer radius minus the inner radius, or the longer one, and the radius, the outer one is this case. Nice straight line there. And then the shorter one. Okay, so this one's a little more complicated though. And because we're integrating about a horizontal line here, about the line y equals 5, we're going to be dealing with vertical lines. So we're going to be integrating with respect to x. Okay, but I just said it was a little more complicated because what we need to do is we need to create an expression that gives me this distance from 5 to this point right here, or 5 to this point, and 5 to every point on this graph of y equals 1 plus the square root of x. So what we do is a subtraction problem. It's the area between curves again. We take the distance of y equals 5, and then the distance of y equals 1 plus the square root of x, which it just depends on where we are. Because as soon as I know the x value, I would plug it in and it would give me this y value. It would tell me the distance right here. So the outer radius is 5 minus this curve. And then that will give me this line right here. If I take a 5, the distance of 5, and I subtract this blue piece from it, it's going to give me this squiggly thing. So this is the outer radius that I'm going to stick right inside here. Okay, so we do the same thing for the inner radius. The inner radius is going to be the line y equals 3. And if you think about it, the inner radius is 2 forever. It's a constant. But it's the same concept where we take the distance from the line of rotation, whatever we're spinning it about, and subtract whatever curve we're dealing with, which in this case is y equals 3, and that'll give us the piece that we need, the radius that we need. Okay, so we have our outer radius, which is 5 minus the curve, and we have our inner radius, which is 5 minus y equals 3. We can simplify this. This is just going to be a 2 inside this one, and this one's going to be 4, because we can do 5 minus 1 there. Be careful, that's going to have to be a minus sign right there. And we're going to square both of those. Okay, hopefully that's not too bad. Let's move on to the integrating. So we're going to need to FOIL this out. So first is 16, last is x. The inside is going to be 2 times negative 4 square root of x. And then we have a 16 and a negative 4 here. Let's combine those. Whoops, went backwards, sorry. Combine those, get a 12, and integrate. So this is 12x, this is x to the 1/2 power, so that'll be x to the 3/2 over 3/2, or x to the 3/2 times the reciprocal of 3/2. And then this will be 1/2 x squared, or x squared over 2. Simplify a little bit there, and plug in that 4. If you plug in 0, you're going to get 0. This is the fundamental theorem. I'm going quick here. I expect you guys to pause and do the math yourself, because this section really just deals with the setup. Integration was chapter 5. Okay, final answer here, 40 pi over 3. So when you're integrating or revolving around a line other than the x or the y-axis, you have to create an expression that gives you the radius that you need. So in this case, I needed a radius that was 5 minus my curve and 5 minus this line here. And that gave me this piece, and that gave me this piece. Hopefully that makes some sense. Let's do another one. Same situation, I changed the equation up a bit so I can get the graph to fit on this page. It's the same idea though. Find the volume of the solid formed by rotating the region of the graph. Y equals the square root of x, the y-axis, the line y equals 3 again, and we're going to go about the line x equals -2. So here's y equals the square root of x. This top one is y equals 3. And now we are rotating around this vertical line. And we're bounded here again still. So we're still dealing with all of this section. This is the piece that we're going to be rotating. And it's going to be around x equals -2. So again, it's going to be another washer situation. There's a big gap here again. There's a gap of 2, and that means 2 on the other way too. So the diameter of our gap is going to be 4. So here's what this picture looks like. Something like that, where it looks kind of like an upside down volcano. And again, it's like cylindric down the center. There's a hole in the middle. So washer situation again. And our outer radius, the longer one, is this curve. Oh, I'm sorry, it's just square root of x on this one. And notice though that our radiuses, love it, our radiuses are horizontal this time. So we need to take this equation and solve it for x, because we're going to be revolving with respect to y here, integrating with respect to y. So we need to square both sides. Oops, put that 2 in the wrong place. Okay, so here's our outer radius. That's one piece of it, but we actually have to add more to it. So in order to get it to touch the line of rotation, we had to create, because like the x value here, when we say x equals y squared, it's measuring it from the y-axis. Same thing here. If we were going to be rotating, let's say, I use this example quite a bit, where this is y equals x squared. Let's pretend that we're integrating this piece right here. Well, when I integrate that, this gives me the distance from this point to the x-axis. It doesn't go any further than that. So if I wanted to go further, if I wanted to revolve this around like y equals -2, I would have to add 2 to it. I would have to add more. You need to make it longer. So in this case, it's the same thing. When you say x equals y squared, you're only talking about this purple distance right here. And because the line of rotation is further away than that, we have to add 2 to it. The inner radius, so the outer radius is going to be y squared plus 2. The inner radius is just going to equal 2 because it's the distance from 0 to 2 here. So outer radius is y squared plus 2, and we're talking x equals, because it gives us this distance right here. This y squared gives me this distance, and then the plus 2 adds on that blue piece. And then the inner radius is just 2. So when we set it up, outer radius squared, y squared plus 2 squared, inner radius is going to be 2 squared. And you have to FOIL that. Y squared times itself, 2 times 2, and then 2y squared doubled. And then minus this 4. So these 4's cancel actually. And we can integrate. Oh, I'm sorry. Let me go back to that picture so we can see why we're going from 0 to 3. 0 to 3 here. That's why the limits are 0 to 3. Okay. Integrate. This will be 1/5 y times 5. Or I'm sorry. 1/5 y to the 5th power. Y to the 5th power over 5. And this will be y cubed over 3. Plug in your 3 and your 0. The 0's go away. Simplify. Common denominator there. This one's probably just easier to use a calculator, right? I probably did that anyway. And your final answer if you simplify it. All right, volume of revolution. So I gave you a disk method revolving around the y-axis, a washer method revolving around the x-axis, that was in video 1, and then we did 2 washers here revolving around a horizontal line that was not the x-axis, and then this one is a vertical line that is not the y-axis. So these take lots of practice. Please watch again. Watch the Khan Academy videos and the Patrick JMT videos and study Forge, please.